This is Mr. Robeson here. Welcome back to Calculus. Today we're looking at section 3.4, concavity. So it's about the shape of the curve, and we'll talk about what a point of inflection is, go over how to find concavity, and then talk about the second derivative test. All right, so concavity deals with how the curve is shaped. So if you look at this one, it looks like this is a parabola opening up. We call that concave up. Right. If you look at this one, it's kind of like a parabola opening down, so it's down facing, it's our sad face, it is concave down. So concave up is the smiley face, concave down is the frowny face. All right, so the way we can find this is by looking at the derivative's derivative. All right, so our derivative here is negative, and then our derivative here is positive, and then our derivative here is more positive. So our derivative is increasing, which means its derivative must be greater than 0. So the second derivative is greater than 0. Here we're going from positive to more negative, so our derivative is decreasing, which tells us that its derivative, or the second derivative, would be less than 0. So that is how we find concavity, as we look at the second derivative of a function. All right, so let's see. Comparing graphs of f and f prime. So this is the graph of f of x. This is the graph of f prime of x. Where is f increasing and decreasing? So we can look here and say, okay, well, it's increasing to -1, and then it's decreasing to 1, and then it's increasing again. So let's see, we're increasing from -infinity to -1. And then we are decreasing from -1 to 1. And then we are increasing from 1 to infinity. I realize we could also put these as closed intervals on all the actual numbers. But now we take a look at f prime. And we say, where is f prime, the derivative, positive and negative? Well, it's positive out here. So it's positive from -infinity to -1. It's negative in this middle section here, so from -1 to 1. And then it's positive again from 1 to infinity. Notice these intervals match up exactly. Like positive, we're increasing, negative, we're decreasing. Exactly the same. All right, now we're going to try and do the same thing with concavity. So where is f of x concave up and concave down? So we often abbreviate this CCU for concave up, CCU. And concave down is CCD. All right, so let's see, we start off, well, that's definitely frowny face. All right, that's our parabola opening down shape. So we're concave down until 0, and then we turn around, and now we're smiley face, so we're concave up. So we are concave down from -infinity to 0, as far as we can tell. And when we are concave up from 0 to positive infinity. All right, so now let's see, where is f prime increasing? So we go over to here, f prime is increasing from 0 to infinity. And where is f prime decreasing? Well, we're decreasing here from 0, or actually from -infinity all the way until 0, then we stop and go up. So from -infinity to 0. So if you notice, the concave down matches perfectly with the decreasing, f prime decreasing, and the concave up matches perfectly where the f prime is increasing. So what's the second derivative for f of x? Well, here's the first derivative. So the second derivative is just 2x. So when is it positive and negative? Let's see, we could set it equal to 0. We're going to get x equals 0 as its critical number. So at 0, it could change signs. So it's negative before 0, positive after 0. So that means our second derivative is negative before 0, positive after 0, which tells us that our function f is concave down and then concave up. That's usually what I use for my symbols. I can also write CCU and CCD like that. All right. And this point at 0 is going to have a special name too. This point is going to be called a point of inflection, but we'll go over that in a second. Like I said, we'll go over that in a second. Right now, point of inflection is a point where the graph changes concavity. So it goes from concave up to concave down, or concave down to concave up. So it has to change. So if it goes from concave up to concave up, That's not a point of inflection. All right, so if it is a point of inflection, then either the second derivative has to equal 0 or the second derivative has to be undefined. All right, so it has to be like a critical point for our second derivative. So let's see if we can find the points of inflection for this guy and where it's concave up and concave down. So to start off, we need to get to the second derivative. So we start off by taking the first derivative. And we get that. We just keep going. There's no reason to stop at the first derivative here. We need the second derivative. So we get 12x squared minus 24x. And now we're going to do just like we did with the first derivative. We're going to set it equals 0. We're going to factor, find its critical values, all that sort of stuff. So we can factor out at 12x. We're left with x minus 2. So we get x equals 0 and x equals 2. So now again, we're going to do the same sort of procedure. We want to know where something's positive and negative. We do our sign analysis chart, our number line chart. So we got 0 and 2 as our points. We've got 12x as a factor, and we've got x minus 2 as a factor. So 12x is negative, oops, should be a 2 here, 0 and 2. Negative, positive, positive. This guy is going to be negative, negative, and then positive after 2. So that means our second derivative, f double prime, is 2 negatives make a positive, negative in the middle, positive on the outside. So that means our original function will be concave up, concave down, concave up. So it looks like we have a point of inflection here at 0 and a point of inflection here at 2. If we wanted to find the actual points, we'd plug it in. So we'd get 0, 0 if we plug in 0. If we plug in 2, we get 16 minus, let's see, it's going to be 32. So we get negative 16. So this is 2, negative 16. And there it is. Yep. So there's our 0, 0. So we're concave up here, then we're concave down here, then we're concave up here, and here's our 2, negative 16, and here's our 0, 0. All right, we could also write intervals for concave up and concave down like we did with increasing and decreasing. So we could say that we are concave up from negative infinity to 0 and from 2 to infinity, and that we are concave down from 0 to 2, like that. All right, more examples. Find concavity, find the point of inflection. All right, so here's our function. So we need its second derivative. So before I actually start taking derivative, I'm going to rewrite this as 6 times x squared plus 3 to the negative 1. All right, it's easier to rewrite it and do it as a chain rule, in my opinion, than it is to try and do it as a quotient rule with just a constant on top here. So we're just going to leave the constant out front here and take the derivative. F prime is, bring down the 1, we get negative 6 x squared plus 3 to the 1 less exponent times the derivative of the inside. All right, so now we're getting negative 12 x squared plus 3 to the negative 2. So now we got some options. We can bring this back down to the bottom and do a quotient rule, or we can leave it as it is and just do a product rule. So I tend to just leave it as it is. I like product rule better than quotient rule anyway, but it's kind of up to you. All right, so if we do the product rule, there's our first, there's our second. So it's first times the derivative of the second, bring down the negative 2. We got x squared plus 3 to the negative 3 times the derivative of the inside, which is another 2x, plus the second times the derivative of the first. The derivative of the first is just negative 12. Second's just going to stay x squared plus 3 to the negative 2. Now, probably the most difficult part is just trying to simplify this thing here. So this is our second derivative. This is what we want to know where it equals 0. But to do that, we need to simplify it. So I'm going to rewrite it without these negative exponents and just put some tops together and see what we get. So we're going to have negative and negative here are going to cancel. We've got an x and an x, so an x squared. And 12 times 2 times another 2, so 12 times 4 is 48. So we get 48x squared over x squared plus 3 to the third. The other one, let's see, we could say plus or minus. Minus. Now I'm just going to put the 12 on top. So the negative sign from the 12 is out here. And we've got x squared plus 3 squared. All right, so now we need a common denominator if we want to put this together. So we need another x squared plus 3 down here. Anything we do to the bottom of a fraction, we also have to do to the top of a fraction. So we're going to get 48x squared minus 12 times x squared minus 12 times 3. Oops, 36. It's 12 times 4. All over x squared plus 3 cubed. And let's see, we can put together those x squared, so that's going to be 36x squared minus 36 over x squared plus 3 cubed. And we can factor out a 36 from this. We're left with x squared minus 1 on top, which if we set this equal to 0 top and bottom, we're going to get x equals plus or minus 1 on the top. The bottom, that never equals 0. All right, x squared is always positive. If we add 3, it's always greater than or equal to 0. If we add 3, it's definitely going to be greater than 0. So we don't have this ever equal 0. This is always going to be positive. So now we do our number line chart. I'm going to do it over here because I think I have a graph coming up over on the other side there. So all we have on here is -1 and +1. On the top, we've got 36x squared minus 1. On the bottom, we've got x squared plus 3 cubed. We could probably leave that off if we really wanted to, because we just said that that's always positive, and always positive does not affect our number line chart. All right, if we plug in a number out here like -2, that's going to be 4 minus 1 is 3. 3 times 36 is positive. If we plug in a number in here like 0, we get -1 times 36 is negative. Plug in a number out here, we're back to positive. So that means our second derivative is just putting these signs together, positive, negative, positive. So that means our original function, since this is the second derivative, is concave up, concave down, concave up. So it looks like if we want the intervals for concave up, it would be from -infinity to -1, and again from 1 to infinity. And if we want the intervals for concave down, it's just that middle section, -1 to 1. All right, and the points of inflection, they're going to be at -1 and 1. So each of these is going to be a point of inflection because it's continuous. So this is going to be a point of inflection, and this is going to be a point of inflection. We just plug them in to get the points. For each one, it would be 6 over 4. So it would be the point 1, comma, 6 over 4 or 3 over 2. And this would be -1, comma, 3 over 2. Let's see, how does that look? There it is. And there's our concave. Let's see, we're concave. It's tough to tell, but it is kind of concave up here. Definitely concave down here. And then it's back to concave up over here. Yep. All right, determine the concavity and the open intervals for which the graph is concave up and concave down. And, well, we're getting tougher with our derivative rules because we can't forget any of our derivative rules. So we're got to do a quotient rule with this guy. I just want to make a note that at x equals 2 and x equals -2, we have vertical asymptotes. So those are definitely not going to be points of inflection, but we can still change concavity there. All right, so it's low d high minus high d low, square the bottom, and away we go. Whew. This may simplify some. Let's see. We're going to distribute a 2x to each one of those, and we're going to combine some like terms. So we're going to get 2x to the third minus 4 times 2x is 8x. Then we got minus 2x times x squared. So that's another 2x to the third. Hey, those are going to cancel. Minus -2x, so that's going to be plus 2x. 2x to the thirds are going to cancel. We can put those tops, this minus 8 and plus 2 together. We've got x squared minus 4 squared on the bottom. So we get that our derivative, -8 plus 2 is -6x over x squared minus 4 squared. Now we need one more derivative. You might be able to hear my garage door opening in the background. Let's see. So it's low d high. So x squared minus 4 squared times the derivative of the top minus the top times the derivative of the bottom. We're going to do a chain rule here. 2 times x squared minus 4 to the 1 less exponent times the derivative of the inside. All over the bottom squared. Well, it's already squared. So squared squared gives us to the 4th. Like that. And now we just need to clean up this top. So the first thing I notice here is that they both have this x squared minus 4, so I can factor that out. X squared minus 4. And let's see, they both have a -6 we can also factor out. So what's left in the first guy? Well, nothing but 1 of the x squared minus 4 because we took one of them out. The -6 is gone. We took out that -6 as well. So then we're going to have a minus. We've got a 2, an x, a 2, an x, so that's 4x squared. And we factored out this x squared minus 4, just like we factored out that one. So nothing left is there. And on the bottom, we've got x squared minus 4 to the 4th. So this one to the first right here is going to cancel with one of these down here and leave us with 3 down there. So we're going to be left with -6 out in front. We can put together the x squared, and the minus 4x squared is going to give us a -3x squared. And we have a minus 4 all over x squared minus 4 to the 3rd. And let's see, we can take out a negative from this. Negative, and it's going to cancel out with that 6 there. And we're left with that. So now we want to know, where does this guy equal 0? Well, if we set the top equal to 0, this 3x squared minus 4 is never going to equal 0 because 3x squared will never equal -4, right? Like something squared was not going to equal a negative number unless we're working with imaginary numbers, and we're not. This is not complex analysis. All right, here we're just going to get x equals 2 and -2, which can't be points of inflection because we already mentioned that they are vertical asymptotes. So we're not going to get any points of inflection, but we can still have changes in concavity. In fact, the whole top's positive. We can leave it off the sign analysis chart if we want. The bottom is the important part here, the x squared minus 4 to the 3rd. It can change signs at -2 and 2. All right, so that means if we plug in a number down here, like -4, and we square it, it's going to be positive, and then to the 3rd is positive. Something in the middle, like 0, is going to be -4 cubed is negative. Something on this side is back to positive. So that means our function f double prime, its second derivative is positive, negative, positive, which means our function f is concave up, then concave down, and then concave up. And these are vertical asymptotes, so they are not points of inflection. So there it is. There's our graph. Concave up over here. Yep. Concave down here. Yep. Frowny face. Concave up here. Yep. There we go. All right. So the second derivative test. So we can use the second derivative to tell if something is a minimum or a maximum. For instance, if it's concave up, so the second derivative is positive, f double prime is greater than 0, means that f is concave up. And if it's concave up and f prime, the derivative, equals 0 at that x, well, then that must be this point down here. That means it is a relative minimum. All right. If our second derivative is negative, second derivative less than 0, and the derivative is equal to 0, then that tells us that we are concave, f will be concave down, and that point must be at the top like that, and that's going to be a relative maximum. If the second derivative equals 0, who knows? Like we could be changing from concave up to concave down like that, in which case it's not a min or a max, or other weird things could happen. We could go from concave up to concave up and have a corner, or we can go from concave down to concave down and also have another corner. But then again, that wouldn't be where the derivative equals 0. That would be the derivative would be undefined. So that'd be a different case. All right, so use the second derivative test to tell the relative extrema for this guy. All right, so first off, we need to take the first derivative, bring down the 5, we get -15x to the 4th. Bring down the 3, we get 15x squared. So first thing we need to know is where are the zeros on the first derivative. So if we factor out a 15x squared, or a -15x squared, we're left with x squared minus 1 equal to 0. So we get 0 and 1 and -1 as our zeros from our first derivative. So those are the points we're going to look at on the second derivative. So now let's take the second derivative. We bring down the 4. We get -60x to the 3rd. Bring down the 2 here. We'll get plus 30x. Now, we don't have to do a number line chart. We don't have to set this equal to 0 and do all that sort of stuff. We just want to plug in each one. So we want to know what's f double prime of 0. Well, if we plug in 0, we're going to get 0. Right. next, what's f double prime of 1? Well, we're going to get negative 60 plus 30 is negative 30. So that's less than 0. So that must mean we are concave down there. So that means that's a max. We're going to have a relative max. And if we try negative 1, we're going to get negative 60 times negative 1. So that's going to be positive 60. 30 times negative 1 is going to be minus 30. So it's going to be 30. It's greater than 0. So that means we are concave up. Oh, that's a relative min. And at 0, it's inconclusive. We're not really sure. All right, so there's the graph. So, yep, sure enough, we've got a relative minimum at negative 1. We've got a relative max at 1. And with 0, it was neither. It was just a horizontal tangent. All right, notice it's not the point negative 130, and it's not the point 1 negative 30. That's just telling the concavity. It's concave up here. It's concave down here. All right, so that was the second derivative test. So we went over concavity, finding points of inflection, finding intervals where it's concave up and down, and then using the second derivative test to tell if something is concave or a minimum or a maximum. And that is the end of 3.4.